from Barclays. I'm going to speak a bit today about how we use Clang to generate code for serialization. When I say generate code, I mean we actually generate the C++ code that we then compile with GCC or Visual Studio. So I thought I'd give a brief introduction into what we do. I guess it's obvious maybe what ARM and what Google do, but maybe not so obvious what a bank like Barclays does with C++ and Clang. So I work in the quantitative analytics library. The library is about 10 million lines of C++ code. I think we all up have about 230 odd developers. Many have PhDs in physics or mathematics. And then there's people like me who are more software engineers there to be the kind of C++ technical people. We deliver this library 2 or 3 times a week to each of the trading desks. And the trading desks have IT teams that plug into the library. And essentially they use the library to calculate the bank's risk, and then they use the library to work out how to hedge against that risk, put simply. Obviously, market behavior and calculating risk is fairly complex, too complex to use closed form methods. So a lot of the calculations tend to be Monte Carlo techniques. And as you know, Monte Carlo techniques, you're looking at running something maybe 100,000 times before it starts to converge on a result. Obviously, this is computationally expensive. We need to calculate risk, overnight or within the next hour or two. This is not high frequency trading or anything like that. But the faster we do it, the better. On a single machine, obviously risk would take days or even weeks. We don't really know, no one's really tried, but we know it would take a very long time to calculate. So for speed, we distribute versions of, we distribute QA or the quantitative analytics library amongst, at the moment, I believe 55,000 CPU cores. Basically a massive grid. To communicate between each of the instances of the library on the grid, obviously we need some way of serializing the data structures in each of the quantitative analytics libraries. And that's obviously where the need for us for serializing these things comes in. So I think at a guesstimate, there's probably 8,000 classes that require serialization in the library, and probably once upon a time, well before my time, maybe the code for serializing those classes was handwritten. Obviously this is time consuming. It's not a very scalable solution. Your maintenance costs increase, prone to human errors. Everybody's going to code their little serialization of their class slightly different. It's hard to enforce standards, and what happens if you want to roll out a new format like JSON or XML, or do it slightly differently, then some poor intern has to come in and rewrite 7,000 classes or something like that. So through sheer insanity or maybe pure genius, before my time, somebody decided to use Doxygen to generate this serialization code. Doxygen obviously being the documentation generator. This slide used to be 3 slides of negatives, but I was asked by one of my managers to cut it down. That's, so obviously Doxygen's not designed with the intention of generating serialization. Doxygen would only run on directories. It wouldn't run on a translation unit like a compiler or something. In fact, if you had an A and B derived from A, and A was in a different directory, but you only gave it the directory for B, it would just completely forget about A and only serialize B. it built up massive data structures in memory, and in fact, when it got to about 2 gigabytes, would mysteriously crash. It was pretty slow. It's not a compiler. The implementation wasn't separated from the functionality of generating serialization. So what I mean by that is what Doxygen used to do is scan the code and look for a declaration, basically, serialize this. This is the serialize function. And then it would find that and write the implementation. But of course, what if you wanted to change the function serialization? Well, then once again, you had to go through and change 7,000 classes. And for various reasons, one being that it only ran on directories, it was quite difficult to integrate with our build system. It was done more as you would build the QA library. Well, sorry, you would complete your code, and then you would run this thing, and it would generate serialization. Then you'd build it, and then maybe it didn't work, so you'd make the change, and then you'd have to run it again. And it just wasn't seamless for our developers. So obviously, enter Clang, and I, for one, was pretty happy when Clang came in to do this. The Clang AST is obviously designed to be easy to use, easy to understand. It's fast, it's accurate. That's a big positive. For example, when we did the Doxygen one, when we converted to Clang, we had to go back and then put the errors of the Doxygen one into the Clang one, so we could verify that it produced the same thing. But now we've moved on from that, and it obviously generates it correctly. A big positive is we can use attributes to say serialize this, rather than using the function declaration that I spoke about earlier. The implementation of the serialization is now completely separated from the functionality, and I'll talk about that a bit more in a second. We can generate customized errors with Clang, obviously, with respect to serialization. It runs on a translation unit, and this means we can easily integrate this into our build system. And we can easily deliver wholesale changes, and if we want to roll out a new format, obviously that's very easy to do, because we just edit our extension to Clang, and it's there. Attributes. Clang has great support for them. It's all the classes are there in the AST to easily query whether a function, a class, a member variable, anything has an attribute on it. And it's very hard to get it wrong. It's hard to mistake in a class that wants to be serialized. And so this is just a little bit of macro code that we have there, using variadic templates to add an attribute to something. So this is a class simple that we want to serialize, and our developers, all they have to do is put this attr serialize there, and Clang's going to pick this up and say, right, I want to generate serialization for this simple class. Furthermore, we can say serialize this class, but for some reason don't serialize this member. And we can just add an attribute to do that. And furthermore, again, for some reason, this developer wants to write their own code for serializing this class. Maybe it's more complicated vector or something along those lines. But the attributes, we can actually add some code there to say, don't generate serialization for this because I've already written it for you. And there's various more attributes that we use, and mainly most of them are to do with templates and things like that. So the problem when we want to generate code for serialization of a class is how do we generate the code for, say, a class like A? How do we generate that serialization code once and only once? Or once at all? So here we have a simple class A, it wants to be serialized, and we're going to pass it to Clang. Clang's going to then generate some C++, And then in a second step, our build system is going to come along and compile that generated code with our code. So the problem that we're going to face is that in any translation unit, we could have B and C, and B or C or whatever could be hash included by another translation unit. And you don't want to generate serialization code for B twice, because then you're going to get twice the definitions and so forth. So we basically have to find something unique about the class A to know that this is the only time we're going to find this about A. So generate code for this serialization now, and B, that'll get taken care of in another translation unit because we haven't found that unique thing about B. So this is further just explaining that now we've got a DCPP, and DCPP is another translation unit, another CPP. It's going to get processed by Clang, and now you've got the problem of B being hash included in two translation units. So what do we do about this? We find what's called a key function. A key function is the function that is going to be unique in this translation unit to A. So you're only going to find this key function once, and it's going to exist only in this translation unit, and then therefore if you've found it, you know to generate serialization code for it now, because you're not going to find it in any other translation unit. This is similar to, so similar in fact, our code looks very similar to the code in Clang and GCC for finding finding a key function for where to put a vtable. So if a translation unit or a class has a virtual function, you want to put a vtable in there. It's the same kind of method, except in our case, we don't care whether it's a virtual method or not. We're looking at serializing anything that has this serialization attribute there. So we're going to find the key function for A now. So what we've already done is our code, which our code's called SourceGen. It compiles directly against the Clang libs, so it kind of extends Clang. And we've gotten this translation unit. We've built an AST for it. We've got the AST, and now we've said to the AST, give me all of the declarations in this translation unit. So we've visited the declaration context of the translation unit. In other words, just give me all of these things. Now we're going to visit each method declaration using, and this is these CXX method decals. This class here is, that's Clang AST code. And we're saying, give us each of the methods in this translation unit. Now, each of the methods that's going to come back, I've highlighted here in red. The reason that you're not getting these methods is because these methods are in another declaration context. These methods here are in the declaration context of A, the class A. And this is in class C and likewise B. So the methods that we're going to get visited back on from Clang, from this translation unit, are going to be these global methods. And what we're looking for is a method that defines a function of A or X or some class, because we know if we can find a definition of a class, then it's probably going to be in the CPP. And it's not going to be in any other CPP, it's going to be in this CPP, which makes it unique to this translation unit. So the first thing I do is basically, this is the iterator, which is iterating over each of these methods. And I say to that iterator, give me the declaration context that this function is in. And you can see that the global function has disappeared because it has no declaration context. It's not in anything. The declaration context of these two functions, though, however, is A, because they're the definitions of a class A. So immediately I've got rid of the global function. Now, why did I want to get rid of the global function? Because the global function can exist in any translation unit. If it's in b.h, anything that hash includes b.h is also going to have that translation unit. So, sorry, just back to this slide. So the next thing I'm going to look at is F1. And I'm going to say, okay, I've found F1. It has a declaration context of A. And at that stage, we say, is this a CXX record decal, which is a C++ class as represented by the AST? And we say yes. So we've found ourselves a class with a function that's defined in this CPP. So we're pretty interested in that class right now. And that's essentially what this piece of code here is doing. Just some simple runtime type information, which is quite common throughout Clang in using it to discover what certain things are. So if we look back one slide, we're visiting the method decal. We get that, and now we're dynamically casting the declaration, which was A F1. We're casting that to CXX record decal, and we're saying, yes, this is a class. The declaration context of this A is a class, so we're interested in that. And so now we're going to look at A and what's in that. So what we need to do now that we've found A is find something that's unique to this translation unit. Now, back on the previous slide, you'll notice I didn't define a constructor, a default constructor for A, or any constructor for that matter. So what the compiler is going to do is it's going to implicitly throw in an A, a constructor for A. Now, it does that inline, so that's going to end up in A.h, and then A.h can once again be hash included by any translation unit. And so therefore, that's not a very good candidate, well, it's not a candidate, for something that's unique to this translation unit. We have to throw that away. And that's essentially what I'm doing going through this piece of code here. If I hit any of these things about each of these methods, iterating through the methods that I don't like, I'm skipping over them. They're not things that are good candidates. F2 is not a good candidate because it's a pure virtual function. It probably doesn't have an implementation, or most probably. F3 is declared inline, so we've got to throw that away, and that's inline specified. F4, someone's put an inline body here, so that could be in any translation unit as well. We've got to ditch that. And so basically we're left with this F1, and when we come across that, we can say, yep, this is something that belongs to this particular translation unit and no other translation unit. So now we know that A uniquely is defined here in A.cpp. And we can generate some serialization code for that. So what happens though when you can't find a key function? I mean, if in the previous example, if F1 wasn't there was no candidates to find a key function. At the moment, we wouldn't generate any serialization code for that whatsoever. It just gets skipped over because Clang would never even find it. But what we have to ask our developers to do if this doesn't happen is we have this little macro which manually you're putting in a key function for Clang to find and pick up. You can see here that it's just the type of the function. It's just a implicit template. And this little trick here, size of t, we're only interested in serializing, well, we can't serialize incomplete types. So that's why we do the size of. We'd get a compile error if this was an incomplete type. We can't generate serialization for those anyway. Right, so now that we've found A, I'm going to talk a little bit about what we do generate. So we've found A, we want to generate serialization, and Clang's going to generate some A.ser.cpp. When that's generated, we basically come along, there's a second step in our build system, Visual Studio or GCC, depending on what you're on, and it essentially force includes that a.cpp. It's just a compiler option. It basically obviously shoves these two files together and the whole translation unit then compiles it, you get a.obj. And now you've got your serialization code inside of there. So you've generated it with Clang and then we compile it with some compiler. And to the developer who's building this, it all happens seamlessly. They don't really see it. The build system comes along, it says compile a.cpp in the background there. a.ser.cpp is generated and it's compiled together. And just by putting that attribute there, all of their code has been generated and compiled in there, and they've got serialization. So for a simple class A, what do we need to know? What goes in a.ser.cpp? Well, we need to know if A has any base classes. And what we generate, we just do these simple kind of traits functions. We need to know if A has any base classes because obviously we're interested in if it does derive from something, we need to serialize that as well. In this case, A doesn't have any base classes. Then we have a declaration for the function of serializing A, and then we have the definition, which finally does whatever serialization does. What happens though when A is a B? Well, essentially it's like a top-down structure. So we'd have to jump up to B and we say, does B have any serialization classes? Base classes? No, it doesn't. And then we write this declaration for B. Then we jump down to A. We say, does A have any base classes? Yes, it does, has B. Then the declaration for A. Then the definition for serializing A. Yeah, so I mean the reason that we have this declaration for serializing B is because obviously something's going to come along and serialize B at some point in time, and it's going to generate the definition for serializing B, and that's why the declaration is there in A, and the linker will fix that up for us. The reason we put that declaration there is because we don't want to introduce some sort of gate or wait in our build system. We want to compile this thing right now. We don't want to have to sit there and wait for B to be serialized and then go, oh, okay, now we can serialize A as well. We want to basically serialize A and then compile it straight away. The serialization for B, here's the declaration. You'll find the definition some point down in the future. So they're simple cases, but obviously it gets more complicated when you start getting into things like templates. So in this case, we want to serialize B, but B has a parameter member T. But we don't really know what T is yet, or Clang could know what T is, but what we choose to do is we choose to also write the serialization as an implicit template. BT. And then obviously the compiler will sort out all the instantiations of BT, whether it's used as T as an int or a double, T as another class, all of those things. I guess the reason we do that is just a design decision. I mean, we could use Clang to sit there and write out, oh, okay, I can see that T's an int, I can see that T's a double, write that. But then you'd be writing the definitions possibly for serializing everything that uses B of T for T in every translation unit that in fact does that. So I guess in this way, we're just writing B of T once, let the compiler do what it does best. So you can see here that we jump up. So we want to know what I think that's actually around the wrong way. Base classes of B of T should probably be first. Is that right, John? Right, no, sorry, yeah, no, that is correct.
For,
yep.
For members, you do base classes of the containing class first.
Yes, yep, sorry, okay, yep. So then we want to know the base classes of B of T. And then we're going to jump into here and serialize this. And then we jump back out and then now we do serialize A, and then the definition for serializing A. So it's a top-down, you jump up, then you jump into it, into the class, write the serialization for that, then you jump out, then you're down here, and then you jump in again, and so on and so forth. There's various other examples. I could go through a billion examples on how to serialize explicit templates, template where you derive from something that is a template, where you have a templated member, all of those various things. But the key is that Clang, you can do all of them with Clang. There's no problem. There's nothing it doesn't know. And it's quite easy to do after, well, about a year of fiddling around. So we're using Clang for various other things other than generating code for serialization. The quantitative analytics library has what's called a keyhole interface. It's similar to COM. Our clients don't want to have to recompile against the quantitative analytics library every week. They probably wouldn't do so, and it would take time. But essentially every call comes through one function. But if that's going to happen and you're not compiling against the library, then you have to maintain some sort of backwards compatibility. And we're using Clang to check that backwards compatibility. So if somebody exposes a function A, you can't just take A away, because then somebody could call A. Or if A has int1, int2, you can't take those away. So we're using Clang to check that all of this backwards compatibility is maintained. Not only that, but we're using Clang to generate all of the boilerplate code between us and our clients. So it's all automatically generated. None of our developers have to write anything to do that. This interface also generates various interfaces, C++, obviously, COM, we use Swig to develop Java. There's a CLR.NET interface, and all of this stuff is going to be generated with Clang in the future. Something else we're using is enforcing standards on the use of the framework classes. There's been various examples where a developer, for some reason, I'm sure you've come across it before as well, you could throw an error right now at compile time, but they're not going to find out till 1.5 hours of compiling, and then another 40 minutes of testing that, oh, right, okay, this silly thing I did back here, I've now found it out 2 hours later when we could have just thrown an error. And we're using Clang to throw compile time errors where we can increase productivity. And there's also been some work on thread safety markup, or even just, this has recently changed more to developing some sort of, well, it's a static analysis for threading and developing a policy to say, right, if you call this particular method, is it thread safe, is it not? Yeah, so I've got 5 minutes remaining, so yeah, that's it. Is there any questions? Yes?
Did you open source the serialization library?
No. No, it's not open source.
Are there plans for that?
I don't believe so. But these slides pretty much tell you how to do it. That's probably as open source as it could possibly get, I think. Yeah, it's not my decision. It's the bank's decision.
Second question.
Yep.
Did you see the work of Chandler of the AST markers?
Yes.
Are you using this type of library to enforce your framework, to enforce your rules
Mm-hmm.
for your static asserts? Or you have developed something completely different?
I believe we've developed something different at this stage, but we're very interested in what Chandler's doing. And it seems like possibly a better way of doing things than how we're doing them now. Yeah. Mm.
Chandler's library was not around when we started.
Yeah, we wish we had this conference a year ago. Yes, you had a question. Yeah.
Can you tell us a bit more about thread safe markup?
I don't believe I can, mainly because I haven't worked on it.
But for example, like, is it used to avoid that there is some data race?
Is it used to?
To try to avoid data race?
Yeah, anything to do with, from what I understand, it's been used to develop a policy. So if you call some function, we want to say to our clients, this function is, we believe this function is thread safe or it is not thread safe. And anything that renders this function non-thread safe, by using static analysis, by using Clang, we'll just say this is not thread safe, and that's one of the examples that it could analyze. Now obviously it gets more and more complicated the more and more threads that you use, to the point where you might just throw your hands in the air and say, we don't even know if this particular line of code is thread safe, so we're just going to tell you that we don't think it's thread safe. But I mean that's a whole nother talk. There's a whole conference there.
I can say a little. We're still researching it. One idea is to extend C++ using the attributes again to be a bit like D, if you ever came across it. It has the immutable concept and the pure concept. So one idea is we can mark up pieces of our code with those attributes. So just like const percolates through the code, we could first of all run our analyzer on our code, and it would tell us what the markup should be. Then you do the markup, and then later when developers come start hacking, you run it in another mode where it says, well, you just broke the contract with this markup. This markup says this is a pure function, but it isn't. But we have nothing yet. Instead, it's a work in progress.
Mm-hmm. Any other questions?
Could you justify why pure virtuals are excluded a bit more? Because if you're at that stage, surely they have been defined, so that issue isn't.
Well, it could be defined in another translation unit, I suppose. You don't know if it's there, basically. I mean, it's most likely that it's not defined.
But isn't this checked when you do have a definition for that function?
Do you have any insight into that, John?
Well, the problem you've got is when you've encountered a method implementation, and then you essentially need to be able to say, the function that I found in implementation, is this the key function of my class? And at that point, we need to be able to say what the key function is independently of what we found. Because, well, I suppose the first method was pure virtual, and the second method wasn't pure virtual, it was a normal method. And they're implemented in different translation units. In the translation unit that's got the pure virtual, if I encounter that method and decide that that's the key function, I'm going to implement it in that translation unit. In the other translation unit, I won't encounter the pure virtual, I'll ignore it and decide that the second function was the key method. I've now got two implementations of it. So because pure virtual methods typically have no implementation, we say it's not valid regardless of whether we found it. It's not valid to be a function.
Mm-hmm. Yep. Thanks, John. There's a question up the back, or no, that was your question?
Explanation was so elaborate that, cool.
Yep.
Key goal is we wanted to be able to run on one translation unit at a time, not to have a link phase where you needed global knowledge.
Mm-hmm. Yeah. Yes.
I have a question. You've taken hand of all the serialization so that the coders can get on with coding.
Mm-hmm.
Do you find that's limiting you to serializing sort of fairly typically struct-like classes? I saw you've got the ways of excluding things from serialization.
Mm-hmm.
Is that a limiting factor to the developers' work?
No, I don't believe so. Well, it's no more limiting, or I'd say it's less limiting than our previous serialization framework, which had limitations. So Clang's allowed us probably, and John can probably touch on this more than I can, but it's allowed us to serialize more things than we ever could before. So as far as I know, these were just 3 basic examples, but there's a whole test suite testing, like I said, explicit template instantiations, vectors, just everything you can possibly imagine serializing. And we've been able to serialize a good chunk of it. Is that right, John? Or yeah.
So maybe where you've got an object with some sort of pre-computed state in it or something.
Yeah.
And you're excluding that from the serialization. And then when you receive one of those objects down the wire and deserialize it, how do you ensure that that state gets sort of populated out? Does that make sense?
Yeah, John's probably better.
2 classes, one for transit over the wire and one where
Mhm.
the logic goes on.
Well, the logic tends to be in methods. The model on which a lot of this works is you sort of do your setup, and then it's for, as Wayne said, it's for distribution of risk computation. So you sort of do all your setup in one place and then distribute everything in a reasonably set up state. And typically, you don't exclude very much from serialization. The best example typically is stuff that purely caches. You might decide that the cost of sending stuff over a wire is more expensive than recomputing it at the remote end. But typically, you just take the whole state of something from one place, put it in another, and then run the computation as many places as you like.
Mhm.
That's your question.
Yep. Yeah, thanks. Yeah. Okay,